Hello everyone, welcome to Learn Overflow. In this video, we will look into this LeetCode problem. The problem says binary tree cameras. Okay, so it also says that this is a hard type problem. Let's not think about that. Let's read what this problem is trying to say with us. It says you were given a root of binary tree, okay, and we install cameras on the tree nodes where each camera at the node can monitor its parent, itself, and its immediate children. Okay, so we need to return the minimum number of cameras needed to monitor all the nodes of the tree. All right. So see, so basically what we can learn from here is like we need to calculate the number of cameras. That is the minimum number of cameras. So whenever we see something like minimum, maximum, or something like to minimize the stuff, the first intuition is you can say going with a greedy approach, right? So before looking what can it be, you can just think of it like that. That it may lie on the greedy line. But let's see more. Let's see on the what are the other test cases we have and how we can actually move ahead with this. Let's see ahead. So if we just look in depth into this examples we have one by one, then what we can see exactly is we have a root over here. Okay, that's the root, and then its left is right. So its left is node, its right is null, and then left right of the first node, like the left of the left. So we have this, and thus we can see that by that example that this one camera is enough for looking after all the nodes. Like if we remember exactly that here we saw that each camera can actually monitor like here it's written, yeah, monitor its parent, itself, and its immediate children. So that means that this camera can monitor its parent, itself, and its immediate children. Immediate children being both the children nodes we have. So it says a binary tree. Thus we know that will be left and right. Only two children will be there for each node, right? Maximum. All right. Then that's an example we have. Let's look at other examples and try to understand how actually they are going ahead with this. Okay. So what is this example two given to us? It says like a normal like tree where mostly all of those are in the left. So we find that it's like there's a root and itself and its children. So this way the particular the first camera is controlling this too, and then we have a camera over here which is controlling its parent, itself, and its children. So you may think the other way around, that maybe a camera at here and a camera at here, like the lift node would also have worked. Yes, would also have worked. Maybe in the case like because like all the nodes are getting covered. So anyways, the output will be 2 bits. So that's all we can think over here. Let's see what else is the expression given for us, right? In the expression it says that at least two cameras, that is yes, at least two cameras are needed. That anyways you can find two cameras, right? And they need to monitor all the nodes of the tree. The above image shows one valid configuration of the camera. All right. What is given to us? It says the number of nodes in the tree is in the range 1 to 1000. All right, we know that the maximum range of number of nodes will go from 1000. So there will be at least one node. That's also been inside over here. All right. Moving ahead, we see that the node val is 0. What does that mean? Node val being 0. Node val is 0. That definitely means that we are not bothered with the value on these nodes. We are all bothered about the placing of the camera. So as the definition of the binary tree being given to us in the LeetCode, you can see there's a value property is there and the left and right are there. So we are not at all bothered with the value property. What we are only bothered with the left and right properties of that. All right. So let's take another example, like our own example, and try to understand how we can actually go ahead with that. So let's have a tree like this. Let's think on this. So in this tree, what can happen exactly? So we see that right, we are out here. So you see that if we put an camera over here, then we actually are covering this one and this one. Let me just change the color. Okay. So if we put a camera over here, so we see that we can cover this one, and this one, right? This is covered. Now we need to cover the other elements also, right? So we find that it doesn't have any children. So this is the last element over here. On this node, if we place a camera over here, we can cover this one, and the parent one that is like already covered for us. All right. Now that is we got this two cameras still now. And then we already know that up to this, all these are covered. So we can put a camera over here, a camera over here, and a camera over here. So we find that the total number of cameras for us is more or less 5. But is it like the optimum solution? Is it the solution they're asking that the minimum number of cameras? Think properly. Is it so or is it not? But I think it is not. How? I will tell you. Let me just erase this in a moment. All right. So look properly. Exactly, if we're going down the line, we find that actually we more or less ended up with having 5 cameras, more or less like maximum we went up to 5 cameras. All right. Let's look. What if we just move up the line, because we find that we put the cameras on this lift nodes, right? This 3 lift node we have here. So we put a camera on this lift node. But if we haven't put a camera on this lift node, we could have saved our number of cameras, because we have a 3 leaf node over here, and that's true for a binary tree, like for a fully grown binary tree, like a complete binary tree, you can find something like this. It will have a complete 2 children. Each node will have 2 children. Okay, so in that case, we'll find the leaf node will always have a maximum number of like the maximum cameras needed to be covered over there, right? That's a complete binary tree. So if I just look into this tree that I drawn just now, look here, how many trees? Like if you target the leaf node being covered first, we are just wasting 4 cameras. But what if we just move one step back and we just have an camera over here and a camera over here? See, being this 2 cameras being installed, we can find this the whole tree can be installed. Thus, we're at least sure that we don't need to put a camera on the leaf node. If we put a camera on the leaf node, unless it is completely necessary, then we know, like, yeah, it's okay, right? We get our like the minimum if we don't put it on the leaf node, like unnecessarily. If it's needed, it's needed. Now let's look into this example we are working over here. In this example, we have like we first of all like went down. Okay, so over here, if we just put a camera over here, okay, let's look. If we put a camera over here, this particular node is covered. This particular node is covered, right? And if I just put a camera over here, then obviously this particular node is covered, this particular node is covered, and this particular node is covered. See, like with 2 nodes or 2 cameras, we actually have covered like a bigger tree, right? That exact concept we are working on this diagram, right? So exactly, we got 2 cameras. Like till now, camera count is 2. Next, look here, we are left with this 2 nodes being covered with camera. Now, if we put a camera over here, it works. Like if I put a camera over here, it will cover up this node and it will cover up this node. Okay, that is the answer. So anyways, we find that camera is 3. That's the minimum we came up. Like previously, so we came up with the 5 cameras, but now we came up with a minimum number. That's what we are asked to do, the minimum number of cameras. Okay, if we try to like have a similarity between our ideas, we are not. So we are kind of like avoiding the parent node, and we are kind of avoiding the root node. Okay, so if we just have a uniformity in your idea, then let's not put our camera over the root node. Let's rather put our camera over our leaf node or the child node of our root node. So this also is getting covered. So anyways, we find that this is a 3 camera setup is working for us. So how will we go ahead with that? So to basically to go ahead with this kind of statement, we can have a greedy approach. Okay, we can definitely have a greedy approach, and I will work on that, on finding out that exact greedy approach and the solution for that. Also, we while doing this video, I just thought, why don't we can do something like an enum kind of stuff to mark each node as being covered, not covered, or needed to be covered, like covered or has a camera, or like it's needed to be covered, something like that. So we can do it. It's more or less a DFS approach. We'll see. The first approach, like the main approach is we need to go into, we'll start from the root node. So this is the root being given to us. Let me change the color. So in our code statement, this is the root being given to us, all right? And after this root, we have this root. So we'll have a left root, we have a right root. So if you just note here that the range, the number of nodes, okay, the number of nodes is in the range of 1 to 1000. Basically, a single node is there, all right? So if a single node is there, so our camera count cannot be 0 in any case, right? So in every case, our camera will be starting from 1, okay? So that's basically usually we have. Now, that's the corner case we're thinking of. Next is, look exactly, we can have, the thing we need to do is like we have a root over here, we'll move into the left. We'll next move into the left and check if this is covered by a camera or not. In case this is covered, like we'll check that if the root is null, okay, let's have a small diagram. Let's think like a node is there, and the left is there, right is there, we have this much, okay? Just a small diagram, just break into this. Now, just this thing, we'll first do what? We'll first, like on a DFS approach, we'll first, see, we don't need a BFS, like a breadth first search. We don't need to look for this and then this. We'd rather need to look into the depth and find out, okay, we've got a null. We should move back from here, that these roots are null. So we should move back to this particular node. And then we should place a camera over here. And thus we should move back that, okay, this is also being covered. And then we find that other node. So that's the monopoly DFS approach. You can see that we need to work on. All right. Next is how will we go ahead with this kind of diagram on a think on a programmatically logic. Okay, how we can do that? If a root is null, okay, say we are over here and then we move to its left, that is null. Okay, fine, this is null. So once we move over here, we found then we find that the root over here is null. Okay, if a root is null, that means we assume that this particular node, that is a null node, is already covered by camera, right? That's null, and we can have a like base case that if a node is null, it's covered, and just go back from here. Okay. Next thing is we can do a check like if its left is like we need to cover its left. Okay. If it's something like that, let me erase this part. Okay. Okay. If it's something like we need to cover is left, it's like its left need to be covered, its right need to be covered. Okay. And if something like this kind of condition is there, like we are on a node, its left need to be covered, its right need to be covered. If that is so, then we are sure that we need to place a camera over here, right? We should like it doesn't have a condition like we place a camera. It's like we need one camera. If our root is there and its left is also not covered, its right is also not covered, then we are sure that we need one camera over there. Just look into this small diagram. What happened over here on this lower diagram exactly? We know that we got two cameras, but once we are over here, okay, over this diagram, so that means its root, its left is like covered, we know, and its right is something that is not covered. So either of the one is not covered, right? So that means on this particular diagram we have, on this particular box, we need one camera. One camera can be placed over here, can be placed over here. It doesn't matter. We need at least one camera for this place. Like if its left is not, like if its nest is not, if its left is not covered, or if its right is not covered, then we need one camera over here. That's for sure. Now, the other thing is, look in a different way. If when we are thinking of this diagram, let me erase this two boxes. Okay. When we were thinking of this part, okay, this particular part, then what do you find? If it means, see, we are over on this particular node. Okay, look carefully. If it's left, we find that its left has a camera, we place a camera. If its right has a camera, we place a camera. That means what? This node is already being covered. We should mark this node that this is already being covered, right? So that is the main concept. If like say its left is covered, not covered, or its right is not covered, then we need to have one camera. If its left is covered, its right is covered, then we need to have like we know that it is already being covered. Else, on like the third case is that if like the third case is there when nothing is there, then we need to do that. We need to cover that area. That is, we need again like we need one more right to that. So we need one more camera to that. Okay, so that's how we will just continue with that. All right, let me put this up here. All right, so here we have this question here. We are just wrapping up over here. All right, so how we plan to go ahead with this? So the first thing we need is the cam count. Like what I'm like the ultimate solution for us is like camera count. Okay, so we say this is 0. This is the camera count, and this is the number of cameras. This is the final answer we should return actually. That's 0. Okay. Initially, we know it is 0. Why I'm marking it 0? It's more like you may ask, like in a few minutes, like I said, we should have a minimum one camera. So we'll have a check that whether this particular node, like the root node, is already covered or not. If it's covered, then it shouldn't be one, like initially, right? So it may give us a wrong answer in that case. So we'll look, like we'll understand this more once I write more code into this. We'll understand this. Next, we are marking our each node as being covered, uncovered, and whether it has a cover, whether it has a camera or it needs to be covered, or it's like it. We need to cover it. Okay, so in that case we'll use we can use a different class extending this tree node and have something additional with it, but that is a bit complex. So we can use an easier thing that we have in Java. Okay, that's the what we call as enum. Okay, that's enum. So what enum is basically, enum is we call it as a special class that represent the group of constants. Like whatever constants we need, we will just add to it, like more like a final variable. So we'll add an enum over here and just go ahead with this concept what we're thinking over here. Like what we will say, public will say enum, and this enum will be the nodes for us. Okay, like whether the nodes is covered, whether the nodes is not covered, and like that. So our enum will have what enum has has camera. Okay, so enum works in this manner. It doesn't need like multiple initializations and all. It's like simple, like it has some final variables with us or final constraints with us. So it's like has camera, like node has a camera, or node is being covered. Node is being covered, or I'm sorry, yeah, or the other case can be we need to cover. Okay, not need cover, need camera. All right, so this is what we actually need as a node. Like each node of the tree node needs this kind of like what we thought, like we can have this kind of concept over here. Now let's move deeper into this. What exactly I'm trying to do here is like let me just add some spaces because it looks good. All right, then we'll have like the first thing is if a root is not covered, okay, then we need to place a camera at the root, right? So this is the condition I was talking about, that minimum it will be 1. So in that case, we need to place a camera over here, and that will do that over this programmatically, not in the camera count being marked as 1. If the root is being covered by some other cameras at some child node, then we will have a wrong answer. +1 answer will be there. So we'll have something like if the root is not covered, we'll have a camera over here. So that means we so basically how we can do that, we we make some like camera count, we can do something like plus, right? So if the root is not null, so we need to have a condition that if the root is not null. So for that, we better say we have a supporting function for us. Okay, I'll just write more over here. We'll have a supporting function that will check whether this is like whether check for each node, like thing like for our Dfs solution, how we used to do. We have a supporting Dfs function for us, and that's exact thing I'm trying to do over here. So it will be more like public. Then we'll have our nodes. Like it will return us this nodes whether it has been covered or it has a camera or has been covered or need a camera. Okay, if, we'll have a return type as nodes, and based on that we'll be do some like we have a Dfs normal Dfs function over here. Okay, we're doing Dfs, and there we need tree node, and this tree node will be well just the name root, the same thing we have over here. Okay, so this is Dfs. Now let's write over here. So we'll be doing something like Dfs of root being the function given to us. If this is a root, double equals nodes dot so our main condition was if the root needs to be covered, or like if the root is not covered, then you need to place a camera, right? So we'll check nodes dot need camera. Okay, if nodes dot need camera, then we will go ahead with plus camera count. Else we'll do a plus camera count. Else it will be the camera count. Fine. That's all we have, and this should be the final return for us, right? All right. This should be the final return that we're checking that if this if the Dfs of root that is returning the nodes and this nodes dot camera count is being returned, then it should be like we should if this needs a camera, then we should increase the camera count. Else our camera count is our answer. So let's see into our Dfs solution. So in the Dfs solution, there will be two things. Okay, we need to try the left child, and we'll be trying the right child subtree. Okay, let's try this out. How? Root dot right. Okay, so this is the first thing we need to do. We need to have like these things down here. But remember, we are doing left dot right, root dot left, root dot right. So at some moment it will be over here, right? It will be over like this particular node for us, right? So if this is at our end node over here, then we need to look for something like it's left, it's right. It will be what? It will move to the left, it will move to the right. So it will be actually null for us, right? So if it is null, so that will be the best condition, right? If it's left is null or it's right is null, it's more like if the root is null, because we are passing the root dot left, root dot right. So it's more like if the root is null. Let me clear this and start typing over here. We can return anything over here. Like we can have written like it has a camera or it's being covered, right? So it doesn't matter because we are just more or less returning back. So since it has a return type of node, so we are just adding something. Like if we return a neat camera, that means like it need camera in any house, we need to add some code over here that if it needs a camera, we need to add camera based on that. But if it's null, so we can definitely say that it's null, so it's covered. More or less, it's covered. We shouldn't be worried about that. Okay. So we are just returning that nodes dot covered. Okay, nodes dot covered. That's been like something we are returning back. More or less, just returning the control back. Now here comes our main thing that we need to do. This is more like what I was saying. Like if any of the child is not covered, then we must place a camera at the current node, right? So that basically means that if the left is not covered, like if the left being returned as like need camera, or the right returns a need camera, that means we should have a camera over there, right? Either if either one have a left or right have a need camera. Let's write this. Yeah. So if it needs a camera, we need to make the camera count as we need to increment the camera count. All right. And once we increment the camera count, then we should actually return back that this particular node has a camera, right? This like it has a camera, so it's more like. So that's the first condition we have over here. Now we need to look into this. Like if anyone on the left or right has a camera, then the current is actually covered, right? It's more like if like over here. Over this particular diagram, we just look, its left has a camera, so it is actually being covered, right? So it's like if any on the left or right has a camera, then that's being covered. Then the root node is actually covered, right? So we'll make a note of that as well. So let's write over here. All right. So it's more like either one has a camera. That means the node, this particular root is actually covered. So we are just returning back. So this is the last condition we have over here, and this is like if none of the children is covering the current node. Okay, that means the current node is not covered by any of the child nodes. That basically means we should have a camera in the parent node, right? So that's our target over here. So if none of this is covered, so it will like return then we should do it like most need camera. All right, so we'll return the final case that if none has a camera, it's like if the other case are not true, then we should do this. So this is the more or less the idea behind this, like behind finding out how this particular one works. Let me just try and run this. It should work actually. Let's see if it has any other errors. Yeah, we can see that this is the base condition is working. Let's use the example test cases and see if they are working or not. Then we can actually go ahead and submit. Yes, this shows like it is working for us. So let's go ahead and submit this case and find out how our code performs. Yes, this code performs definitely well. So that's an normal idea that we can have over here. Okay, let's put it down. So this is the idea behind this. So we are using a Dfa solution. All right, that's all for this video. I hope I can make you understand how this day 17 of the LeetCode daily coding challenge question was, and how you can actually solve this on like thinking on this. If you have any doubts or anything related to this solution, just go ahead and comment below. I'll be happy to help you out. And thank you all for watching this video. Make sure you just subscribe to this channel for more videos like this. Thank you.